Hello everyone, I'm Yogesh Rawat from University of Central Florida. I'm an assistant professor here, and today I'll talk about the MEVA system we have developed here. We call it Gabriella. In our team we have Professor Mubarak Shah. We have PhD students Rizvi, Praveen, Ayush, Kevin, Ur, and Ishan. The problem is we have untrimmed security videos and we have to detect activities. The activities can be from human as well as vehicles, and they can be indoors as well as outdoors. The activities can have just single actors, or they can have multiple actors where they are interacting with each other. There can be actor-object interactions as well. And what we have to do is we have to detect the spatio-temporal localization, which includes the start and end timing of those activities. And we also need spatial extent, where these activities are happening in the video frame. However, the evaluation is not done on the spatial extent. There are several challenges in this problem. First of all, we have untrimmed videos, and there can be multiple activities happening at the same time step. And these activities can be of varying length. Some are very short and some are very long. There can be multiple actors taking part in the same instance of the activity. There can be interactions, such as there can be actor-object interaction. For example, if a person is opening a car door, then he or she is interacting with the door. We can have actor-actor interaction. So these are like activities where we have multiple actors. For example, in the scenario where a person is purchasing something, so these two are interacting with each other. Uh, since these are surveillance cameras, we will have multiple scales of activities, and some of the activities which are far away from the camera will be very tiny and hard to see. So here's one sample which shows like some of the activities happening in the foreground, like close to the camera, and we have some activities very far away from the camera, very hard to see. And the data set is very unbalanced. We have some activities for which we have very few samples. So this shows the distribution of the activities in the data set. Now, most of the existing works which focus on activity detection, they're based on region proposal approach. The issue with region proposals is that performing or extracting these proposals for every frame in the video, that's too memory intensive, and we will have scaling issues. The main concern is if we have multiple actors taking part in the same activity, then how will we pair those actors to the activities? So that's a non-trivial thing. The other approach is using object detection. We can perform this detection on every frame of the video, which will take a lot of time. This is time consuming. And again, the same issue. If we have multiple actors taking part in the same activity, then how many and which actors do we consider to classify that activity? To address some of these issues, we propose a two-stage process. What we do is we take long untrimmed videos and detect activity tubelets directly from the video. And then these detected tubelets are then classified for the activities present in those tubelets. We have a encoder-decoder based architecture which directly take video as input and directly detect for the whole video. So we don't have to do any region proposal. Again, since we are taking the full video as input, we'll have video level detections, and we are not performing any object detection on frame level, and we directly operate on RGB videos, and we don't have to compute any optical flow. So this is an overview of the architecture which we have. I will walk through like each component of this. So what we do is we take the untrimmed video, we divide that into smaller clips, and then each clip is passed to a localization network, which has like a encoder-decoder architecture. We do have skip connections and feature pyramids as well as address conditions to make this more efficient. And to make the activity tublet localization in videos feasible, we propose a multi-layer patch dice loss. I will go through this in detail. So the issue with directly detecting the activities in video is that we'll have lots of background pixels and we'll have very few foreground pixels which are part of activity. So dice loss is one way to resolve this issue, which tries to balance the pixelized classification, and it tries to balance like the foreground as well as the background regions in the frame. But the issue is, since we can have multiple activities present at the same time, so the activities which are far away from the camera, which are very tiny, those will be totally ignored even if we use a dice loss, because some of the activities which are in the foreground, they will be too big, and both of them will be part of the foreground. So to resolve this issue, we propose a patch-based dice loss. This is the normal formulation of a generalized dice loss. What we do is, instead of taking the full frame, we extract patches and then compute dice loss on those patches. To make this loss more efficient, what we do is we extract patches at multiple scales. So right now we are using 3 different scales, and these are like 3x3, 5x5, and 7x7. We combine all these 3 scales together and we assign like equal weights to all these 3 terms to compute the loss. Now using this network, we get foreground background detection for the input clip, and these foreground regions detect the represent the activity tubelets. Here we have some sample examples. So here we can see that, sorry, so if you play this, so if car is moving around, so that's like a activity tubelet which we detect. We have here, so if we have multiple instances of the activities or multiple activities, we can see that we can detect multiple tubelets at the same time. This is another sample where we have humans instead of vehicles. Person coming out, so we can detect these activities in form of tubelets. And since these are performed directly on video level, so this is more efficient than performing object detection at each frame. Now with this foreground background mask, what we do is we extract these activity tubelets, and then these activity tubelets are passed to action classifier, which assign activity scores to each of these tubelets. Now to get final detection, since some of the activities will be very long, some of them will be very short, we have proposed a TMS algorithm, this like post-processing step, which tries to connect these activity tubelets together. And the way it does is, if the activities, if the tubelets belong to the same activity, then it tries to merge those. And if we have a single tubelet in which we have multiple activities, so in that case, it tries to split it. And finally, we get like these detections where like each tube is an activity instance, and this can be used for evaluation. So that was our full architecture. Now I will briefly cover like the real-time system we have developed, which uses that architecture to like run in real time. So this system takes the set of videos, and we have a main process which actually manages all the GPU threads. It also performs the task distribution, and we have 4 GPUs. So the main process actually initializes the models, and it distributes like all the videos it receives to the GPU threads, and each GPU will have a local copy of all the models. So we don't extract frames and save them into disk. We directly load them into memory without extraction, and we have a fail-safe system which uses like 2 different codecs, FFmpeg and OpenCV, just to make it fail-safe. The most time-consuming step is pre-processing, where we have to resize the video frames. So that's the bottleneck right now. And transferring frames to GPU is actually memory intensive as well. So what we do to resolve this is we design a 3-stage buffering mechanism. So we have one buffer for high resolution frames, the second buffer for low resolution frames, and a third buffer for tube proposals. I will walk through this. So this high resolution buffer is the frames which we are directly extracting from the videos. We resize these high resolution frames into low resolution frames, which are used by the localization network to detect the activity tubelets. And we use the coordinates extracted from those tubelets to crop these high resolution buffer frames to extract the activity tubelets. And then these activity tubelets are passed on to the action classifier to make the detections. And finally, these detections are passed to the TMAS algorithm, which performs post-processing for the final detections. So in terms of speed, the system is pretty fast. It runs at around 100 frames per second. And the best model we have right now, it performs a bit slower than this because we have ensemble of like different models, which makes it slow. And in terms of performance, currently it's the best performing system on the leaderboard. Next is going to present the results, so I will not talk about the numbers. But here I have a plot which shows how we have made progress over time. So we started working on this problem in September 2019. We started with a score of 0.84 partial ADC score, and currently we are at 0.36. Here we are showing some sample visualizations of the detections. So we can see that multiple activities are happening at the same time and all are being detected. So here we have like person interacting with another person. We have a vehicle reversal. Then again we have here right turn and a left turn. So we have another example here. So let me play this. So what I want to show here is that activity is happening too far away from the camera. It's pretty small. And even if there is occlusion, the spiller is like occluding that car, the prediction was consistent, and that's happening because we are detecting at video level instead of frame level, so we don't have that issue of occlusion. There are some limitations of this approach. So we have a two-stage approach, and we need connected components to extract the activity tubelets. So the question is, can we merge these two stages together and get rid of this connected component? So what it will do is it will not only make the system more efficient, it will also improve the performance because both extraction and detection, both extraction and classification will be performed at the same time. The other limitation is if we have multiple instances of any activity happening close to each other, we'll have single activity tublet for those because we are not actually separating different instances, but we believe this can be easily done and we'll focus on this as well. If you're interested in like more details, we have archived paper on the system. You can refer to this link. And finally, we would like to thank like a number of groups which were of great help during this progress. So first of all, we'd like to thank like all the groups which provided the annotations. University of Maryland, Professor Raman Group, which provides us like the first set of annotations. Carnegie Mellon University, Professor Alex, also provided like initial set of annotations when we started working on this. Kitware and then IBM. We would like to thank NIST for all the evaluation they have done. They were very responsive and they helped us a lot like in evaluating our systems in time. And finally, I would like to thank ARPA for funding. Thank you.